For those who have studied physics, one of the first things you learn is probably that there are certain quantities that are conserved in an isolated system. The conservation laws that dictate these quantities are sort of like the fundamental rules of our universe, and if applied correctly, makes that one pesky problem in your physics problem set so much easier. You may be quite familiar with some of these well-known conservation laws and what they tell us. Conservation of charge is the basis of electricity and magnetism. Conservation of linear momentum dictates the motions of collisions. Conservation of angular momentum tells us how planets orbit their stars. And conservation of energy can be applied to, well, almost any situation. In fact, the law of conservation of energy is so important that it's the basic assumption of the Schrödinger equation, the most fundamental equation in quantum mechanics. However, the all-important quantity of energy is actually not conserved on a universal scale. In fact, it's changing as you're watching this video. And this is caused by the constant expansion of the universe. How? Well, the cosmic inflation changes the energy of the universe in two ways. One is the obvious fact that there must be some sort of energy that's causing the universe to expand throughout its entire history. This expansion energy also seems to be getting stronger as time goes on, as astronomers observe that the expansion rate of the universe is currently accelerating. In fact, the increase in energy of this expansion is so strong that it now dominates the composition of our universe, more so than normal matter and dark matter combined, and many of you may know it by its other name, dark energy. The other way in which energy is changing due to the expansion of the universe has to do with the intrinsic relationship between light's wavelength and energy. You see, the energy a light wave carries is tied to its wavelength, with higher energy light waves having shorter wavelength and lower energy light waves having longer wavelengths. However, as you may imagine, when a particle of light travels through the expanding universe, its wavelength is stretched out, thus causing it to lose its energy. This effect has been dubbed redshifting, since it will cause visible light to drift towards the red end of the visible light spectrum where there is lower energy. Since each of the two effects of the expansion of the universe decreases and increases the total energy of the universe, it may be reasonable to assume that these two fluctuations balances each other out and the total energy of the universe is overall conserved. But in reality, the contribution of dark energy far outweighs the energy lost due to the redshifting of lights. The question is, why? Why is energy, one of the most important conservative quantities we take for granted on a small scale, not conserved on a cosmic scale? Well, to better understand why, allow me to present an analogy. Imagine a car driving down a continuous straight road that seemingly goes on forever. We know that the momentum of the car is conserved since there is no force in the direction of the car's movement. The only force present here is the downward gravitational force pulling the car down the road. However, this condition can easily be broken. For example, if we now rotate the plane of the road so that the car is going uphill on a slight incline, we now see that we have to apply a force to oppose the constant downward pull to keep the car going at a constant speed. If not, the gravitational pull would continually pull the car downward, and therefore the conservation of momentum is violated. Now this is easy to see on a 3D plane. However, if we looked at the whole setup in the perspective normal to the plane of the roll, it would paint a familiar picture. If our whole perception of the world is in the 2D world, we would just experience a constant force pulling the car in the opposite direction of its motion, not knowing that it's only a component of a gravitational force that requires an additional plane of space to understand. This could be analogous to our current understanding of the expansion of the universe, where scientists are still trying to figure out a cause for expansion. In this analogy, the car could be the light particle in our universe. Whereas the car is constantly losing momentum in the direction it is traveling in, the light particle in our universe loses their energy as they travel through the expanding space. Just as the loss in kinetic energy of the car is tiny in comparison to the gravitational energy of the planet producing the gravitational force pulling the car downhill, the loss in energy of the redshifting of light particles is significantly less than that of dark energy. But as you may notice that in this analogy, the car is not in an isolated system. We must include the whole planet to get a wider picture that the overall momentum is conserved. In fact, the whole setup of the car on the road is just a tiny speck on the planet, and in turn, the planet is just a minuscule part of the galaxy, and so on and so forth. With each system, we may see it as complete and all we have to consider, but in actuality, it's just a tiny part of a larger world. Perhaps this is the same case as our current understanding of the universe. There may be a larger underlying cause to why our universe is expanding, and by taking another dimension into consideration in our car scenario, we must find the same missing piece of puzzle to truly comprehend the mysteries of dark energy. Along the way, we will likely uncover more about our world that we would have never imagined, and a lot more mysteries for future scientists to solve.